Guys, Mr. Bowman here. We're looking at 2.16 probability methods, and in this video we're going to focus on the merit questions from the 2016 exam. So from the website we're starting off with question number 8, and I've given us a bit of a hint that it's related to do with probability trees. It will be a bit of a messy question, but we'll get there. So trees from the Brookhaven apple orchard are harvested twice a year. Records from the previous years have shown that 70% of the apples are picked for the first harvest, 35% are picked for the second harvest. Once the apples have been picked, they've said, well, 9% are going to export, 31% are going to the local market, and the rest are sent to the factory to be made into apple sauce. What proportion of apples will be sent to the factory to make that apple sauce? We're going to start off with our tree, and the first thing we need to think about is how do the events sequence in terms of like a timeline. And for the first harvest, that's what we're looking at. The apples can be picked or they could not be picked. The probability of them being picked were 70%, which is 0.7. So 0.7 over here, 0.3 down the bottom. We're then going to move on to the second harvest. If the apples have been picked, well, they're not going to be picked again, so we don't need a branch there, but we will need a branch down the bottom to determine if the second harvest, the apple were picked or not picked. And in this case, we were told 35% were picked. So that there is 0.35, meaning 0.65 will be down the bottom. If they are picked, where do they go? So where do they go? Question mark. And there's a few different options, and the tree is going to be a bit messy. So from the first branch, they could be exported, which they said were 9% or 0.09. They could be sent to the local market, which was 0.31, and then finally, the one we're interested in, they could have been sent to make sauce, which would have been the leftover 0.6. The same apples down here for the second harvest, same proportions, could be exported, which was 0.09. It could be sent to the local market. I'll just call it local this time, 0.31, or finally, could be sent to the factory to make sauce at 0.6. So that's our pretty messy tree. Going back to the question, we only care about the ones that were sent to make sauce, so we care about the ones ending in the sauce options. So let's get into the math side of it. So the probability of the apple being sent to make sauce will be equal to the addition of those two events. So this one here, or the first one up the top there, that's going to be 0.6 and 0.7 multiplied together. So 0.7 times 0.6. We're then going to add the second option down the bottom, which is 0.6, 0.35, and 0.3, all multiplied together. So 0.3 times 0.35 times 0.6. When you get them into your calculator, the first combination is going to be 0.42. The second combination, a lot smaller, 0.063. And finally, you add those together to get your final answer. 483 is the probability that a random apple from the tree or from the harvest or from that orchard is going to be turned into sauce. We're now on to question number 9. And this question here was deceptively true. It looked easy, but deceptively hard. So I think a lot of us would have gone down the wrong route by mistake. So we've got a two-way table discussing conventionally grown apples, organic apples, versus if they're diseased or not. And our question was, if there was 171,000 organic apples, notice that is not total apples. Based on the sample, how many would you expect? So I like to see that a word expect because we know that's going to be the expected value formula. How many would we expect to be conventionally grown and diseased? So to find this, normally you're given the n value, but this time around, we're given a number. That's not the total of apples though, that's just a total of the organic apples. And you also need to find the probability of the thing you're interested in, which case is the conventionally grown apples. Let's start off with the probability. So probability of, I'm going to write con for conventional and D for diseased. That's going to be F over T. And conventionally and diseased apples, that's that 122 up there, and the total 1200 down the bottom. And when you put that into your calculator, you should be getting 1017. That had a 4 dp rounding. So just noting, the rounding here, because we're dealing with such a large number of apples, will affect your answer slightly. But however you round, as long as you state your answer and you're consistent with it, you'll get your marks. We now need to find the N value, or the total, and this time around, we've only been given these organic apples. So what we're going to do is, so N will be equal to 171,000 of the organic apples divided by 560. So that'll give us the ratio of organic apples. We're then going to multiply that by 1200, which means we're going to ramp it up to the grand total. And when you do that, I'm getting 366,429 apples. And that there I deliberately rounded to 0 dp, or the nearest whole number for apples, because you can't have part of an apple. And then once we've done that, we've now got the N value, we've now got the P value. We can go ahead and calculate the expected value. So the expected value is going to be equal to N times P, which is equal to 366,429 times 0.1071. So those are the two numbers we've calculated above. And that there will get us to 37,266 apples. And again, that was rounded to 0 dp. So just noting, this answer here will be slightly different to the model answers in the exam, and that was because we rounded to 4 dp instead of 3 dp. So our answer is probably going to be a little bit more accurate because of our more accurate rounding. We are now looking at question number 10. And again, it's a two-way table one. And this time around, just noting, we've been asked about jazz apples and diseased apples. So when you think about your two-way table, we've got diseased, but the other variable, organic or conventionally grown apples, that's not relevant for our question. So this is the type of question where you've been asked to come up with your own or your new two-way table based on the two variables you are investigating. So there's my new two-way table. And firstly, it's jazz apples, and the other type of apple is a beauty apple. So I'm going to call it a B over there. And then the next one here, diseased or not diseased. So your variables might be switched around. That's all good. You'll get the same answer. And then we'll just add on a bit more. We know our grand total is the same, so that's going to be 1,200 apples. And we know 180 are diseased and 1,020 are not diseased. 180 and 1020. This is when we're going to go back to our numbers. So they were told us that 890 apples were jazz apples. So there's 890, which means there were 310 beauty apples. And finally, 182 beauty apples were not diseased. So beauty and not diseased, that number there is going to be 182. Now work backwards to find out any of those missing three numbers. So this number over here will be 310 minus the 182, which is going to get us to 128. Number up here is going to be 180 minus 128, which is going to get us to 52. And the final number is going to be 890 minus 52. That's going to get us to 838 apples. So we've now got a new table in relation to the two variables that we're interested in, the jazz type and the disease. So we now need to get into the probability. So what is the probability? I'm going to write J and D. That there is going to be F over T because we're dealing with two-way tables. Total is 1,200 apples. How many of them are jazz and diseased? That's just those 52 up there. So we're going to put 52 on the numerator. 52 divided by 1,200. 0.0433, and that there had a 4 dp rounding. And our final question, question number 11 from the website, Apples are sent to a factory to make sauce and then they are bottled. So that's the new part. Testing showing that the bottling machine when the bottling machine is operating correctly, we're going to have a mean of 310 and a standard deviation of 4.5. Quality control identifies when the bottle sauce are overweighed, so maybe that's when they're putting too much sauce into each of the bottles. And when the bottle machine is functioning correctly, 1 in 20 bottles is overweight. So 1 in 20, that's secretly a probability, which would be 0.05 or 5%. If more than 1 in 20 bottles are overweight, the machine needs to be adjusted. How many grams of sauce will the bottle contain before it is considered overweight? So we're looking for grams of sauce, so that's going to be the x variable along the x-axis. So as we do for all normal distribution questions, we draw down our curve and write in what we know. So we know that the mean was 310, and we know that the standard deviation was 4.5. So we want no more than 1 out of 20 bottles to be overweight. Overweight would be the bigger end of our scale. That means this area here would 0.05, and that number x will relate to the grams of sauce in each of the bottles, and that'll help us determine if the machine needs adjusting or not. So now that we've done that, we've got to think about our calculator. So we're in the inverse mode, and the first thing you need to input is your tail, and our graph is a left. Oh gosh, that's definitely not the left. Our graph is a right tail because it's on the right-hand side. The area is 0.05. That's the 1 out of 20. The standard deviation, nice and easy, 4.5, and the mean, 310 grams. When you put that all into your calculator, you're going to get 317.4 grams. So when the bottle, or when the bottles are containing more than 1 out of 20 above this number, the machine isn't working properly and it needs to be adjusted. So that wraps up all the merit questions from the 2016 exam. Hopefully you found them useful. Now let's keep practicing, let's keep revising.